Hi, I'm Agah Karakuzu. I'm a postdoc at Neuropolar Research Lab in Montreal. And in this educational session, I'll talk about the role of open source software and community standards in making MRI a comparable modality by reducing multicenter variability. This is a spinner gift box game known as Bean Boozled. Now I will use beans out of this box to introduce what quantitative MRI offers. In this Bean Boozled game, jelly beans with tasty and disgusting flavors look alike. So you spin the wheel, then pick up and eat a jelly bean. For example, brown beans taste like cappuccino or like liver and onions, or these white ones may taste like a birthday cake or like dirty dishwater. So now imagine that we spin the wheel to pick a green jelly bean. They taste either like grass or lime, which is the desired aroma here, and we have 50% chance of picking what we want. So if we can stick with imagination here, quantitative MRI could help us do better than 50%. If we scan the beans using conventional MRI, such as a T1 weighted image, the odds are still the same. Of course, we can see through them in this case, but there is nothing specific to either flavor. But if we had a quantitative MRI method that is sensitive to citric acid, then we could tell lime from grass depending on the content. And the quantitative maps would look like this, and you would set a numerical threshold here because the voxel values now have a meaning, and then you could pick up the good ones. So thanks to quantitative MRI, we could win in this game. And about MRI and jelly beans, you'd be surprised that there is real research using quantitative MRI for tracking moisture distribution in jelly beans. On Monday, the bean is uniformly soft, so we see a uniform % moisture distribution. And on Friday, we scan the beans again and see that the moisture migrates towards the center, forming a crispy crust and a chewy center, which is the desired texture. And this is another powerful feature of quantitative MRI. We can track longitudinal changes on an objective scale of measurement. Here's the Bean Boozled game of quantitative MRI in brain research. We are looking at 3 hyperintense MS-related lesions on a conventional MR image. Here, we cannot distinguish between demyelinated and inflammatory lesions, and this is a quantitative map of G ratio of the same patient. Based on the normative range that we know, we can set a threshold at 0.8 to spot demyelination, which should appear in hot colors. So side by side between the flare image and the G ratio map, only one of these lesions show demyelination, which is a big added value. And this is an example longitudinal follow-up of MS patients using a much simpler metric, T1. Here we see a 4% change per year at TOPS, and the significance map highlights some of these regions, but the study reports that conventional contrast didn't indicate a notable change. So quantitative parameters capture something that weighted images cannot, but in this case, the meaning of those numbers is a bit more obscure. Still, whether we are talking about G ratio threshold at 0.8 or a 4% change in T1, we need sensitive and specific quantitative MRI biomarkers for reliable comparisons. And speaking of sensitivity, when we look at the literature on the relationship between T1 and myelin histology, prediction interval of for R-square ranges from 0.07 to 0.99, with an estimate of 0.53 on average. And similar numbers for yet another relaxometry parameter, T2, and other metrics of MT and diffusion. You can take a closer look at the interactive version of this analysis on neurolibrary.org and reproduce these numbers, but in a nutshell, what we see here is that almost all these quantitative MRI biomarkers are statistically equivalent in myelin imaging, and this points to a considerable variability in quantitative MRI experiments. So based on the literature, I think we can say that quantitative MRI is a collection of amazing methods that are trapped in a maze of variability. To achieve what food science has achieved for soft sweets in soft tissue by using quantitative MRI, we need to find a way out. And this is only possible if we can establish measurements that are comparable across time points and imaging sites. One of the key take-homes of this educational is this figure. Quantitative MRI has a variability problem no matter which quantitative metric is in question. And as it is not difficult enough to find a way out, at some level there is a proprietary blindfold that doesn't allow us to see everything that contributes to our measurements. So quantitative MRI software design should treat this as a core problem and address it at every level of the workflow, not only at the processing step. And that's why I had this ambitious aim of opening and controlling all the components of the quantitative MRI workflow that matters to stability from acquisition to publication, before making our methods better, faster, and stronger, because sometimes a step backwards opens a new path forward, and we believe that the way forward is comparable MRI. At the data processing level, I developed QMR Lab and QMR Flow and took the lead of quantitative MRI bits to establish a community data standard. At the acquisition level, I developed QMR PulseSec that are open source MRI pulse sequences under version control on GitHub, and we recently showed that combining these solutions do reduce variability and named this open and vendor neutral approach to quantitative MRI Venus, coming from vendor neutral sequences. And finally, on the publication front, there is NeuralLibre. It is a preprint server for interactive data analysis where you can reproduce what you calculated at the scanner site in a web browser. Now let's take a look at the components of a quantitative MRI method. This cube represents a conventional MR image, and to create a quantitative MRI dataset, we select or develop a pulse sequence, then we obtain a set of images by systematically manipulating the image contrast. Here we start with an SPGR sequence and acquire 4 images at different flip angles while keeping all other parameters fixed. And collection of these files creates a quantitative MRI dataset. Next, we need a mathematical description that explains the change in the voxel brightness in relation to the parameters we manipulated, and this is called a model. For example, with this data, we can calculate T1 based on the model here. Finally, to estimate parameters, we need to fit our data to the model, and this is typically achieved by solving an optimization problem. So QMR Lab is mostly concerned with implementation of the models and the processing methods, because we cannot compare methods if we cannot reproduce them in the first place, and in addition to providing a code base, we need to offer user support to promote community engagement. And both for users and the developers, a good documentation is key to sustain and improve an open source project. So QMR Lab removes these clouds of poor reproducibility, bad user experience, and the lack of documentation to encourage external contributions to our codebase. QMR Lab is written in MATLAB to make gathering available methods easier, because most of the quantitative MRI implementations are still in MATLAB. It comes with a comprehensive documentation for users and developers along with example datasets. And if you search quantitative MRI on GitHub, you get 76 results. About 15 of them are software packages maintained for the service of the researchers. And when sorted by popularity, QMR Lab comes at the top with 100 stargazers. It is downloaded nearly 500 times on MATLAB File Exchange, and we have more than 20 contributors, and QMR Lab is being used by a variety of disciplines. With QMR Lab, you can run simulations, noise and sensitivity analysis to optimize your quantitative protocols, and of course, you can fit quantitative maps from real-world data. It has a graphical user interface that allows you to access all the features without dealing with scripts, where you can also quickly analyze your data using an ROI toolbox. We support 23 different methods under multiple categories, including diffusion imaging, relaxometry, magnetization transfer, QSM, and field mapping. And it has a full-fledged continuous integration and deployment mechanism in place. This makes it easy to deploy QMR Lab on cloud and on supercomputers under version control. But when QMR Lab started, there were 4 to 5 open source packages for quantitative MRI, but as of today, there are at least 13. These are developed in different languages with various applications in mind, and this made me think again, how can I bring quantitative MRI under one umbrella now there are so many of them? Obviously, we need interoperability, which happens when there is a common language, and proved by the last 6 years, the language we need is the brain imaging data structure, BIDS. Developing a data standard for quantitative MRI was a real challenge Given the large number of methods, with each method coming with a set of different input, output, and metadata and unit requirements, and that's probably why it took our extension proposal nearly 5 years to finalize, but it's now available on the main specification page. Now I'll show a BIDS example for MP2 range for T1 and double angle for B1 mapping. So this MP2 range file collection groups together 4 nifty images and 2 JSON files. Images are reconstructed for magnitude and phase at 2 inversion times, and this determines the naming entities that you see here, inv and part, which are under the NAT directory. And double angle B1 mapping has the file collection name TB1dem, and it includes 2 images acquired at 2 flip angles, which are under the fmap directory, and these are called the file collections. We can use QMR Lab to generate quantitative maps from this dataset, and there's also a proprietary CMAS component that calculates a unique uniform T1 weighted image from this MP2H file collection, and the derivatives are organized as shown here. Quantitative MRI map units are standardized, supplemented by JSON files that contain provenance record whenever possible. And this is the vocabulary of the file collections using inv, part, and flip parameter indexing entities, and all the metadata requirements are defined on a method by method basis with all units and field names standardized. And this is the directory tree for the derivatives. The output metadata informs us about its inputs and how that data was processed. So having a standardized input-output convention makes software more user-friendly and minimizes user errors. For example, without BIDS, it takes at least 11 lines to load the data, set the protocols, and to fit the data and to save the results. With BIDS, it's just 3 lines with the same entry points across models, and these output follows a community data standard, which comes with all these advantages right out of the box. But as I noted before, standardizing data processing covers just one layer. If you imagine a neuroimaging study as a planet, then we create a planet per research, a paper. In the end, each paper is a world of its own, and they all have multiple layers. On the surface, we have statistical analysis and data visualization. If we make this layer transparent by publishing integrated research objects, then we see the next layer, which is processing. Thanks to open source tools, we can make this layer transparent as well, and QMR Lab is just one of these tools. The next layer would be quality control, to trace back issues rising to the surface back to their origin, which is image reconstruction. There are really powerful open source solutions for reproducible reconstruction tasks as well, such as Gadgetron and BART. And then when we went the extra mile to make all these layers visible, what do we need to integrate them? What holds a paper together? I argue that we need community data standards and reproducible execution environments working their magic in a data-driven workflow. So to create fully transparent papers from scanner to publication of integrated research objects, I developed QMR Flow. It's a container-mediated and data-driven quantitative MRI pipelines that are powered by Nextflow. Here's an example QMR Flow. It starts with the conversion of case space into isomer data format, and then it calls Gadgetron to perform reconstruction and converts data into QMRI bits format. And this is followed by motion correction using elastics, and finally, again, QMR Lab for performing T1 mapping. Nextflow is platform agnostic. You can run it locally on any operating systems. You can run it on clouds and high-performance computing clusters as well. Plus, it can consume data directly from cloud storage providers. And QMR Flow follows these 3 principles. The first one is that workflow logic is decoupled from the orchestration of the processes. In other words, these workflow descriptions are declarative. And the second is that each process is executed in its own container. This way, we don't install all our dependencies in one environment. So this is isolating dependencies at the execution level, which is another good software practice. And finally, we use data standards. This way, the data-driven declarations are also standardized across different research labs. With all these principles, it takes a single command to process an entire bits dataset, and when the job is completed, you get a beautiful interactive execution report in HTML format that you can publish through your GitHub pages easily from the same repository where your workflow declarations are. You can easily make quality control an integral part of your pipeline, and you can export intuitive summaries about your analysis. And this is a simple summary of what QMR flow is. But up to this point, the core layer of a paper was hidden in the background, which is data acquisition. To make this layer transparent and to standardize quantitative MRI acquisitions, we developed QMR PulseSec, which are MRI pulse sequences that you can download from GitHub to your GE or Siemens scanners and run them to acquire your experimental data. When we combine QMR PulseSec with QMR flow, we go from papers to a planet where quantitative MRI is standardized. That planet is Venus, which stands for vendor-neutral sequences. Venus is designed to solve a 3T problem. First, to bring transparency to all the elements of the pulse sequence implementations, then to play identical pulse sequences on scanners from different vendors, and finally to develop user-friendly quantitative MRI protocols. We achieve this by combining our open source solution with RT-Hawk real-time imaging platform, which is approved by FDA for clinical use on Siemens and GE scanners. Then we developed a vendor-neutral sequence for magnetization transfer imaging that gives a T1 map and two MT-related maps. Then I scanned a reference T1 phantom and 3 healthy participants on 1 GE and 2 Siemens 3 Tesla clinical scanners, first using a vendor-native MT set protocol, where we equalized the acquisition parameters between scanners as much as possible, but of course there were some inevitable vendor-specific differences. Then we deployed our vendor-neutral MT set implementation on these scanners, where all the acquisition parameters were identical, and on top of that, the vendor-neutral outputs were isomer data and bits ready. In the magnetization transfer ratio maps of one participant, we can clearly see that the vendor-native numbers from GE are higher than those coming from two Siemens scanners, and when we image the same subject in same scanners using Venus, the maps become more comparable across vendors. The same goes for T1. GE native shows an overestimation, but maps from different vendors show better agreement using Venus. MT set is MTR corrected with a T1 map. Therefore, combined effects from these maps contribute further to a vendor-native bias, but again, vendor-neutral maps show superior agreement. When we look at the coefficient of variation in white matter, the same trend holds true for each participant and across participants. Inter-vendor variability is reduced for each quantitative MRI map. But coefficient of variation doesn't tell much about the nature and the scale of these differences, which is another key take-home of this educational. We can use software at multiple levels to reduce variability, but we need to apply informative statistical analysis to explore these effects throughout the relevant range of our biomarkers and on their original scale of measurement. Hierarchical shift function is one of those methods. It calculates differences throughout the distributions at each decile, then overlays individual shift functions to show an overall trend. We see that for T1, intervendor differences reduce from 22 to 6%. In the MTR comparison, again, we see a reduction in intervendor bias throughout deciles when Venus is used for data acquisition. And finally, for MT set, the differences between GE and Siemens reduces to 2.3% from 25.6%. And for another important observation, we can look at the changes in the shift function shapes. Vendor-native bias increases with higher MT set values, showing an exponential curve. On the other hand, vendor-neutral differences show a flatter shift function. And again, we couldn't make this observation if we use statistics based on point estimations. In conclusion, we show that vendor-neutral sequences coupled with fully transparent workflows decrease inter-vendor variability of T1, MTR, and MT set measurements. You can visit the interactive Jupyter book at qmrlab.org/Venus for interactive figures and to reproduce the analysis.